Today we have the pleasure to have with us Marianna Annunziatella from the Centro de Astrobiología in Torre Juan de Ardoz, Madrid. Marianna received her PhD in physics from the University of Trieste in 2016 under the supervision of Dr. Viviano and Professor Girardi. During her PhD, she focuses on the study of cluster galaxies at intermediate redshift, analyzing photometric and spectroscopic data in the optical and near-infrared from both ground and space-based instruments, such as VLT and HST. After her PhD, she had a postdoc at the University of Trieste, followed by a postdoc at Tufts University in Boston, US. And since 2020, she has been a postdoc at the Centro de Astrobiología as a Attrazione Talento Fellow. Her research is now more focused on the study of ultramassive galaxies at high redshift, between 3 and 4. Since 2018, she is part of the Massive Ancient Galaxies at redshift beyond 3 near-infrared survey, which successfully targeted what is now the largest spectroscopically confirmed sample of ultramassive galaxies in this redshift range. Since 2021, she is part of the MIRI GTO program, aiming at extending the discovery and analysis of massive galaxies at higher redshift. Today, Marianna will present her work titled A Look into the Early Stages of Formation of Massive Galaxy. So thank you very much, Marianna. The floor is yours.
Okay, thank you, Enrica, and thank you so much for having me here and give me the opportunity to give this talk. So as you mentioned, I am part of different collaboration, and actually today I'm going to talk about the work that I did and I've been doing here in Madrid at the Centro de Astrobiología with Pablo Pérez González and a lot of collaborators there, but also I'm going to talk about a little bit about the work that I did and I've been doing with my US collaborators. So what all this work have in common is that they both focus on the study of massive galaxies. And in particular, the motivation behind these works is that since now it's almost 20 years, it has been shown that in the local universe, the massive galaxies that are present in the local universe actually started to form stars very early in the universe. And this has basically sparked a search for massive galaxies in different redshifts, thanks to the advent of many near-infrared surveys, both using ground-based facilities or HST data. Here you can see only some of the examples of the most recent years. But of course, now we moved in what we can call the JWST era. And now the discovery of massive galaxies has been pushed at even higher redshift. Here in particular, you can see some candidates at redshift almost 6, but there have been also some higher redshift candidates, for example, the Van Dalton ones. So one of the things that we know about the massive galaxies today is that they are inside the highest density regions of the universe. For example, they are often inside galaxy groups and galaxy clusters. However, what is the environment of these galaxies at higher redshifts has not been studied in detail so far. So here comes the basically the background of the work that I did in this recent year, and the work was just published but has been accepted for a few months on MNRS, and here you can see the QR code if you are interested. And in particular in this work, we wanted to study if there was a correlation between the self-emission histories of massive galaxies and the environment in which these galaxies live. So to carry out this work, we took advantage of different data sets. In particular, we basically selected the galaxies within the Good North field. Why we use the Good-North field? Because in Good-North we have both candles data, which means both basically multi-wavelength photometry from HST, but also grism data in the H-band. And we also have a wealth of other photometric data going from the ultraviolet to the IRAC photometry and also the spectrophotometric photometry. Moreover, in Good-North was also observed by the medium-band large program at the GTC called SHARDS. So these galaxies also can count with medium-band photometry in 25 filters. So in this field, we selected our sample of massive galaxies, where in this case we identify as massive galaxies above 10 to the 10 solar masses. So this threshold usually varies between because it can vary if we have larger or smaller fields. In this case, we had to keep this threshold quite low because we have a small field of view. And we chooses to focus on galaxies between 1 and 1, redshift 1 and 1.5. As I said before, these galaxies can count with HST grism data and GTC medium-band photometry from SHARDS. The other important thing is that more than 50% of our massive galaxies have a spectroscopic redshift, and the other very important thing is that for all the galaxies in this field, in this redshift, so not only for the massive ones, we have very accurate photometric redshift, thanks to the grism and the medium band photometry data. So as you can see, both from here, but better in this plot, our galaxies span quite a different range in the star formation rate. And in particular, you can see here that half of our sample comprises basically star-forming galaxies, so galaxies that are between 3 sigma from the coeval main sequence, and the other half, more or less, of the sample comprises what we can call quiescent galaxies, so galaxies below the 3 sigma from the main sequence. We also have a few star-buds galaxies, so galaxies that are very star-forming. One thing that one has to take into account about this plot is that you can see here the star formation rate, and this star formation rate was derived by not from NSCD15, but from the combination of the ultraviolet and infrared photometry from MIPS and SPIRE. So, and this will be important in a little bit. So we decided we fitted the multi-wavelength data for our galaxies using basically a stellar population synthesis model fit and using Chabré IMF. And here, here you can see an example of one of our fits. You can see here that this galaxy can be fitted by 3 degenerate models, which are degenerate because they are indistinguishable by using only their DSCD. So what we did in this case was to use the SHARDS medium band data and also part of the grism data to derive the basically the stellar indexes, the D4000 and the magnesium UV. By obtaining the stellar indexes, we were able to see which of the models could reproduce better these indexes. And in particular, in this case, you can see that the model that better represents the measured indexes is the third one, that if you see here, it was also the less statistically significant one. We also made use of the information that we have in the infrared, in particular the information in 24 micron. And basically, we discard all the models that predicted a flux in the 24 micron above the sensitivity limit for the galaxies that are not detected in that band. So keeping all that into mind, we derived basically the star formation histories of each of our galaxy, and in particular the mass weighted ages for the galaxies in our sample. Here you can see a plot which is distance from the main sequence of our galaxies as a function of the mass weighted age. And you can see that there is quite a nice correlation between the two quantities, of course. So on one hand, this is to be expected. On the other hand, this is a proof, a kind of a proof of the goodness of our fit, because as I said before, the star formation rate was obtained in a way that is independent from the SED fitting. So here you can see that basically all the galaxies, the young galaxies, so galaxies that are below 0.5 gigayear, are also very star-forming. Galaxies with intermediate ages can be either star-forming or quiescent, and the majority of the galaxies with higher mass-weighted ages are also quiescent. And here you can see a color composite image of some of our galaxies. So for this reason, we decided to derive the galaxies in three different classes, so young, mid-age, and old galaxies, using the same threshold that I just mentioned. So if you see here, so basically the young galaxies are the least massive. They have basically the shorter formation timescale, and they have the higher star formation rates and the higher excision. If you can see in this plot on the left, we plotted the number density of our galaxies and compare it with the number density of star-forming, quiescent, and in general all the galaxies in this redshift range from Msun et al. 2013, and see that there is quite a good agreement between the quantities. And the other thing that we see is that if instead we plot the number density of quiescent galaxies at redshift 2, this is mostly consistent with the number density of all the galaxies. And this could mean that the quiescent galaxies at redshift 2 are the progenitors of our sample of all galaxies. So even if we have a small redshift range to study, still to compare properly galaxies at different redshifts, we decided to derive also what we call the mass-weighted formation redshift that you can see here in this plot. Of course, mass-weighted formation redshift and mass-weighted ages are correlated, are very well correlated. Nonetheless, we decided to divide our sample in three classes according to the formation, the mass-weighted formation redshift. And you can see the three samples here. So we have galaxies with mass-weighted formation redshift below 1.5, galaxies with mass-weighted formation redshift between 1.5 and 2.5, and galaxies with mass-weighted formation redshift above 2.5. And in this plot, you can see that if you plot the median star formation histories of the galaxies in this sample, you can see that the galaxies with mass-weighted formation redshift above 2.5 started to form stars very, very early in the universe. So going into basically what was the main objective of the paper was to study the relation between the star formation histories of our galaxies and the environment in which the galaxies live. So we were able to do that, as I said before, because we have very, very accurate photometric redshift. So we could get a very accurate determination of the environment. And for that, we used three different, even if somehow related estimations. So in particular, we basically derive the environment in three ways. So using the number density within a fixed aperture with an aperture of 1 megaparsec, or using the surface mass density within the same fixed aperture, or calculating the number density based on the distance of the third nearest neighbor. Here you can see a qualitative plot. I'm going to show the more quantitative one in the next slide, but here you can see basically the map of the surface mass density in our field, and overplotted the location of our young, mid-age, and old galaxies. So you can see here that, as we expect, our massive galaxies trace the dense region in the field. However, if you focus on the old galaxies, so in this case on these two red points, you can see that they seem to avoid the most dense region in the field. So here you can see the same result in a more quantitative way. So we plotted the environment versus the mass-weighted formation redshift, and you can see it here for the three different environment estimators. And you can see that while basically galaxies that form below with mass-weighted redshift below 2.5 can be found in even the highest density regions, galaxies that we formed earlier are not found in the most dense regions of the field. One thing that I should point out is that here you don't see very high density field because of course we have a very small field of view, so we don't have structures like clusters, for example. Okay, so since basically you can see here that the results obtained in using the three different environment estimation are basically all in agreement, we now focus on the ones that can be obtained using the surface mass density. And we kind of take an alternative approach. So we have our sample and we divided it in three different regions, and the lowest density region, the intermediate density region, and the highest density region. So if you go to then calculate the median star formation histories of the galaxies in these three regions, you get this, and you can see that while for the lowest density quartile, the star formation histories of the galaxies start much earlier, while for the galaxies in the redshift in the highest density quartile, the star formation history basically doesn't start until redshift 2. We also wanted to see if there was an effect of the environment on the general star formation activity of the galaxies in our sample. So we focused only on the main sequence galaxies, and we studied the main sequence in the three different regions, but we found that there was no influence of the environment on the star formation activity in the three regions. So we also tried to see whether similar results can be obtained also using basically numerical simulations. So to do this, we use the Lastris numerical simulation, in particular the mock ultra deep fields. So we use this because in this case we were able to obtain for the simulated galaxies the quantity in the same way that we obtained them for in the observed data. And here you can see the resulting plot where the basically the simulations is the gray area, and you can see that there is an hint of a similar trend in the numerical simulations. However, you can clearly see, and this could be important to understand what are the process that somehow are not functioning in the simulation. You can see that the simulations really miss two different galaxy types. So the very young galaxies, so galaxies with very low mass-weighted formation redshift, but also very old galaxies, and also galaxies with very high formation redshift. So as the last check that we did, we wanted to see if there was a correlation between star formation histories, environment, and also the morphology of our galaxies. In this plot, you can see the basically the surface mass density of our galaxies as a function of the radius of the galaxies and the SFH index of the galaxies. And we did this basically using the information that were derived by Van der Waal et al. In 2014. And you can see here that if you focus on the galaxies that have the highest mass-weighted redshift, so basically the red and orange points, you can see that on average they have a smaller radius and they have higher SFH index in the H-band. And this is a plot that more or less summarizes these two trends because it's a plot of the basically surface mass density of the galaxies versus the basically internal mass density of the galaxies, which can be derived using the galaxy stellar mass and its radius. And you can see here that if you focus on the galaxies that are on the right hand of the dashed line, the dashed line identifies the galaxies that are compact. And you can see that the majority of old galaxies, of galaxies with higher mass-weighted redshift, are also compact galaxies. So in conclusion, we can see, we saw that basically all massive galaxies avoid the very low density regions, but more interesting, we found that the very high density regions are occupied by galaxies with lower mass-weighted formation redshift. We saw a similar trend in the simulation. However, this trend has to be taken with basically a grain of salt because there are some problems in the last simulation because they don't reproduce entirely the properties of observed galaxies. So what is the future? So as you can see from this plot, which was the plot shown at the beginning, so basically this work heavily relied on the use of grism data, and in particular the grism data from the HST was basically successful to detect continuum galaxy, the continuum of the galaxies down to a magnitude of, I don't think you can see it, down to basically a magnitude of 22. However, now we are entering, so we entered in GWST, in the GWST era, and GWST provides two instruments for the wide field slitless spectroscopy, and one is NIRIS, which provides grism spectroscopy between 0.8 and 2.2 microns in the JH and K band, and the other one is the NIRCam wide field slitless spectroscopy, which provides spectroscopy between 2.4 and 5 microns. And this also means that we will be able to also target galaxies at higher redshift. So this is an example of what has been done with basically the earliest data that have been available for from the GLASSIERS project. And here it's a galaxy that at redshift of basically 2.6 from Marchesini et al. 2023, where you can see that you can definitely recover the continuum with the grism data. And you can see here that the magnitude of these galaxies is around 23 in the H-band, which means these galaxies is already one magnitude fainter than the galaxies that we have successfully observed with HST. And here you can see the what is the ability of the grism spectroscopy to really constrain the properties of the galaxies in terms of ages and, for example, formation timescales. So there are some NIRIS wide field slitless spectroscopy available for cluster galaxies from the ERS project. However, another important set of data is the one that comes from the MIRI GTO, And in particular, so the Miri GTO program 1283, so it observed, as it's in the title, the one region of the good south field with Miri, but it also has a very deep NIRIS parallel program, which imaged and got spectra for another region in the good south. And you can see here from this plot, so this is just some preliminary data that we got, and we just got it in December. So basically, these galaxies, it's a galaxies that has an H-band magnitude and redshift of 24. So it's basically one magnitude fainter than the ones that was the one that was detected in the GLASS project, and it's also 2 magnitudes fainter of the ones that have been used so far with the HSD grism. And you can see here that we are definitely able to recover the continuum of these galaxies, and these galaxies has also a photometric redshift of 3. So this means that we can really extend the range in redshift that we can target. So moving on to the second part of the talk, so I'm going to focus now on what we can call ultramassive galaxies at redshift between 3 and 4. And this work has been done basically within the magazine collaborations, and the results that I'm showing today are taken from these, basically these 3 papers that we did. So the magazine collaboration, where magazine stands for Massive Ancient Galaxies at Redshift Greater than 3 Near Infrared Survey, is a survey that aims to target basically ultramassive galaxies either in the video field or in the cosmos field. So in the video field, so far we have targeted the XMM part of the video fields, which are these XMM 1, 2, and 3. And for this field or fields, we have constructed multi-wavelength photometry over basically 4.5 square degrees. And this multi-wavelength photometry have photometric points from the basically UV to the IRAC imaging from SERVs. So, and we also observed galaxies in the cosmos by considering galaxies in the general cosmos ultravista field, which is a field that has been imaged in 30 photometric bands, but also considering galaxies in the deeper stripes of the cosmos ultravista DR3. And also this field can count of a great wealth of auxiliary data for galaxies from the ultraviolet to the IRAC data, and we can count with almost basically 50 photometric points for each galaxy. So what was the strategy of our survey? So basically we decided to target galaxies that we define ultramassive. So galaxies with stellar masses in log greater than basically the 11 solar masses. So galaxies greater than 10 to 11 solar masses. And you can see here that we focus on the redshift range between 3 and 4. And in this redshift range, with the instrument that we use, which is MOSFIRE on board of the Keck, mounted on the Keck telescope, we are able to target several lines. So we impose also a cut in magnitude, which is of around 21.7, because we wanted to be able to detect the continuum of our galaxies. So we selected a sample of candidates, and then we really visually inspected to only keep galaxies that have a very accurate photometric redshift and also very good SCDs, and also galaxies that have very clear imaging with no clearly present neighbors. So here it's a summary of the galaxies that we observed. So we observed basically 17 galaxies, and we confirmed the redshift of all of them. And you can see the example. And you can see also the position of the galaxies in the UVJ diagram, which is usually used to divide the galaxies into quiescent and star-forming. And you can see that the majority of our galaxies is found in the quiescent region of the UVJ diagram. Here you can see the plot of the star formation rate versus mass for the galaxies in our sample. And you can see that there are basically, we have half of the sample that are really quiescent galaxies, and other galaxies that can be can still be classified as star forming. However, they don't have really high star formation rates. So here it's just a plot showing how accurately we were able to basically estimate the redshift and the masses of these galaxies. So the interesting results that we got for these galaxies was that these galaxies, all of our galaxies seem to have formed the external masses already by redshift between 4 and 6. However, if you can focus on the red on the red panel, you can see that our galaxies didn't quench until more or less redshift 4. This means that these galaxies quenched within the last few mega years of observations. This could be an observational bias because we were basically forced to target only bright galaxies, and galaxies that have been quenched for a longer period of time can be basically can be fainter up to a magnitude fainter, so we would not have targeted them. And this was what in 2020, but I think it still is the most massive spectroscopically confirmed quiescent galaxies at high redshift, at redshift 3.5, and we confirmed these galaxies by observing it in the H and in the K band. And the interesting thing of these galaxies is that if you see here in these plots, we plotted the position of these galaxies in the star formation rate versus mass diagram at different redshifts. So at redshift of observation, which is the second panel, and at higher redshift. And we compare the position of these galaxies with the position of the galaxies at the same redshifts from the illustrious simulation. And you can see from this plot that while at the redshift of observation, our galaxies is within the range of properties predicted by illustrious, even if it's clearly at the edge. If you focus on, for example, at redshift 4, you can see that the star formation rate of this galaxy is way below the star formation rates predicted by the simulations. So this means that in the simulation, there is no quenching mechanism that is so effective that quench these galaxies rapidly enough. And the other interesting thing is that you can see in the next panel, sorry, is this one. You can see that if you plot the position of the dusty star-forming galaxies at redshift 5, you can see that the position of these galaxies and the position of our galaxy are more or less in agreement. This could imply that our ultramassive galaxies, so that dusty star-forming galaxies can be the progenitor of our ultramassive galaxies. So the last bit of work that we did for the magazine so far was to study the velocity dispersions of our galaxies, of our quiescent galaxies, and compare it with that at lower redshift. So in particular here, you can see the velocity dispersion that we obtained and also the velocity dispersion that have been obtained at basically a similar redshift from other work. And one thing that you can notice here is that our work, how our sample really increases the size of the sample at redshift greater than 3. So one thing that you can notice here is that so our galaxies all have large velocity dispersion, confirming the nature of massive objects, and also that there is a similar positive correlation between the velocity dispersion and the stellar mass of our ultramassive galaxies. So we also wanted to investigate the mass size relation and later the dynamical mass of our galaxies. And here you can see the mass size relations for our galaxies, and you can see here that our galaxies are definitely more compact than galaxies at the same mass at lower redshift. One caveat here is that the sizes of our galaxies have been measured by using some tools, but have been measured mostly using ground-based images. And here you can see the plot of dynamical masses versus velocity dispersion for our galaxies and lower redshift counterpart. And you can see that basically our galaxies prefer lighter IMF than their low Z low redshift analogs at the same mass. Preferring IMF that are more similar to the salpeter ones. So as I said, this work was done taking a lot of different precautions, let's say, but nonetheless using the ground-based images. But we got accepted an HST proposal to observe the galaxies in our sample that did not have HST imaging. And we started to observe these galaxies, and probably we will complete the observations by basically the before half of this year, so basically before June. So there are a number of projects that are still ongoing. So first of all, as you remember, I show you the UVG diagram. So we basically chose to target the galaxies that were very close to the basically quiescent edge of the UVG diagram. Even if we chose to observe, we had to observe some sub-forming galaxies, especially in poor weather conditions, or let's say less good weather conditions. So there are still a number of galaxies that we have observed that we haven't observed in what is the most sub-forming region of the UVG diagram, and to observe them, we got approved GTC proposal that with the mirror that will be probably carried out this year. The other thing is that we also observed some of the galaxies in the right corner of the UVG diagram, upper right corner, where there is this red star. And basically, there will be a paper coming soon for that as well. We saw that a lot of the galaxies in this right corner basically constitutes the most massive galaxies in our sample, but it is also mainly constitutes by lower redshift interlopers. So these galaxies that were selected between 3 and 4 are actually at redshift of around 2.5. And this probably can have a big repercussion on the determination of the mass functions that have been determined so far using photometric data. Another thing that we did was to try to move at higher redshift. So first from the ground by spending quite a lot of time on candidate at redshift 4.7, and we were able to confirm the redshift of this candidate, and you will see also for this the paper soon. And this candidate was selected in the video field. And the other thing that is going on is that we got approved a GWST proposal in GEO1 to observe a sample of ultramassive galaxies at redshift 5 from the Cosmos data. So, and that proposal, I think it will be carried out. It will be they will be observed very soon with NIRSpec. So, of course, we will submit a bunch of new proposals for this cycle. So stay tuned for new results. And I think that's it.
Thank you very much, Marianna. Very interesting results. Lots of work there. So we have some time for questions. Maybe to time. Well, I have a couple of questions. When you show the relation between the velocity dispersion in the high redshift sample with respect to the stellar mass, could it be due to the presence of outflow, or how you can explain such a high velocity dispersion?
Yeah, I mean, that could be, but so now we don't have the data to investigate that. So we submitted some nephew proposal for some of these galaxies. So we will be able to tell some. Hopefully, we will be able to tell something if that proposal gets accepted. That's what
the derivation, the kinematics of these galaxies.
What? Sorry.
You are planning the derivation of the kinematics of these galaxies. Nice. Yeah. And
hopefully.
And about the lower redshift sample, I was wondering what is the role of the AGN feedback in the formation of quiescent galaxy?
So basically, okay, so one thing that is so we think that the AGN feedback can play a role into, of course, get these galaxies quiescent. However, so this, I mean, this is this is better studied at lower redshift. However, at higher redshift, this is a process that has to happen very quickly. So we have to still investigate the time scales of this process. And that's also why basically there are still a lot of ongoing projects that try to find quiescent galaxies at always higher redshift. But for sure it can play a role. In the lower redshift, of course, there could be that, like for low redshift galaxies, some of the galaxies could be made quiescent also by environmental processes, so not only intrinsic ones. But yes, at higher redshift, for higher redshift, it could be one process. Yeah.
Thank you. So I think we don't have no more questions on YouTube. No. So I think we can stop here. Thank you very much, Marianna.
Thank you for having me.
And see you next week with the other seminar.
Yeah.
Thank you.